In this video, we will be using SOHCAHTOA to solve right triangles. And we'll just do a few more examples from the packet. So let's start off with this example here where we have triangle ABC where side B is listed as length 6, and we're given angle A to be 40 degrees. And this is another very common thing with trigonometry, is to label the three corners of the triangle using capital letters ABC, to which we refer to the angles, like for example, angle A we would call as the angle, whereas side A is going to be across from the triangle due to the respective nature of how triangles work. And this is how we do it with the law of sines, which we're going to talk about in 5.3. But notice how angle B is up here, but side B is here. This is just a very common way of doing it. So like if this is angle C, we would often refer to this as side C, as like capital versus small letter. So if I wanted to label this triangle, I'll go ahead and call this side C using a little c, and this is side A using a lowercase a. But if I'm considering what I know about this triangle, this is always where I would begin if I'm trying to figure out this triangle. Again, my goal would be to solve, well, what are the two unknown sides and what is the unknown angle? But actually, I forgot to do this in the last video, but one thing is if we already know two angles within a triangle, the third is always very easy to solve using what we refer to as the interior angle principle of a triangle. And that's that the three angles within a triangle always have to add up to 180. I'm not going to review about like exactly why that property is true. It's fairly easy to prove in geometry, but basically the thing about a right triangle that there's another property which I wanted to review, which is the property of complementary angles, which is actually where the sine and cosine get their cofunction name from, is due to the complementary nature of a right triangle. But notice that obviously if it's a right triangle, one of these angles has to be 90 degrees. But the other two angles, since the sum of all three of them have to add up to 180, what this implies is that the other two must also add up to 90. Because if this is 90, these two also must be 90 to make a total of 180. So like in this case, that means that this angle B has to be 50 degrees because those two angles must be complementary. And this is just another term I wanted to review, complementary angles. Not like a compliment, like, hey angle, you're looking acute today. That's a very bad angle pun. But complementary, like they help each other, or whatever. But two complementary angles exhibit the property that A plus B must be equal to 90 degrees. Basically that they add up to 90, or together they form a right angle if they were put together. And you could kind of imagine shifting angle B to right there. And if you put them right next to each other, those two angles together would form a right angle. It just sort of makes sense, because if this one's right, then those two together must also be right. But anyways, basically, the summary of what I'm getting at is that when you let me erase all that. When you are finding, if you have an angle within a right triangle, the other angle you can always solve by subtracting from 90. 90 minus 40 is 50 due to the complementary angle principle that, 90 degrees minus A is equal to B by solving the same formula that I did before. And actually, basically, the third angle is very easy. But from here, notice that I know one of the sides of the triangle, but the other two are unknown. And this would be a place where a lot of people would get stuck if they didn't know, well, what do I do? How do I find those other two sides? Because I could use the Pythagorean Theorem, but I only know B, I don't know A or C. But basically, this is where SOHCAHTOA comes into play. If you know an angle and one side of the triangle, you can always use SOHCAHTOA to find another side. And the question is, well, which function should I start with? Should I start with sine or cosine or tangent? But it's all about what side of the triangle I know. In this case, I know the adjacent side to the angle. So I want to use either tangent or cosine because those two involve the adjacent. I don't want to use sine because if I was to use the sine of theta here, I don't know the opposite and I don't know the hypotenuse. That's not a solvable equation. But if I was to start with the cosine function, cosine, and again, this is always true for any right triangle, as an extension to the definition of trigonometric functions. And really, this helps us see one of the uses of another one of the many uses of trigonometric functions is for working with triangles. But cosine is always equal to adjacent over hypotenuse. And in this case, I know the adjacent side is b. So cosine of, I know the theta is 40 degrees because that was given to me, and I know the adjacent side is 6. So the only thing that is left unknown is the hypotenuse. Let's go ahead and call that c because that's how I've labeled my triangle. But basically, I plug in what I know, which is that theta is 40. That looks kind of like a b, doesn't it? I'll try to make that look a little 6-ier. But basically, I know the adjacent side is 6. I know theta. And the only unknown I have in this equation is c. And from here, I just want to solve the equation for c. And basically, what I could do is I could cross multiply by c. So that would give me c times the cosine of 40 degrees is equal to 6. And then I could divide by the cosine of 40 to find, well, what c must be. C must be 6 divided by the cosine of 40. And cosine of 40 is something that, again, I can't use the unit circle to solve this because 40 degrees is not an angle that I have on there. But I could quite easily type this into my calculator and solve, well, cosine of 40, calculator can solve the cosine of any angle and any position, which just having memorizing the unit circle only, it helps us understand how the trigonometric functions work, but it only goes so far. Because, I could just type in the cosine of 40, again, assuming I'm in degree mode here, and that just gives me, well, whatever the ratio is for that particular angle. And if I take 6 and divide it by that number, it will, reverse the ratio and figure out, okay, well, what must the hypotenuse be? The hypotenuse must be approximately 7.83. I'll go ahead and label it. And it gives me one more piece of the puzzle. And basically from there, I have a couple ways in which I could solve the last unknown side of the triangle. I could either use the tangent function to find a because I already know the adjacent side and would be trying to find the opposite side, or I could just use the Pythagorean theorem because once I know two sides of a triangle, the third is always solvable via Pythagorean theorem. And I think the Pythagorean theorem is a little simpler, but you could use a different trigonometric function to then find the opposite side. But, just whichever way you feel like doing it, I feel like using the Pythagorean theorem here. And technically, this is not an exact answer because here I've approximated the value of c, and if I'm going to use that in another calculation, I want to just make sure that I'm aware that this is not going to be precise, but which is why I recommend to not round your answers too much, because if you round this answer, the next answer that you get is going to have that rounding error, and it could be compounded in this case because I'm squaring something which is rounded. But basically, that would leave me with a squared is equal to 7.83 squared minus 6 squared. Or if I just took that answer that I had previously, squared it, and subtracted 36, 6 squared, that should give me a squared is approximately 25.35. And then, of course, I could take the square root of that to solve for a. And so that would leave me with a is approximately 5.03, which again, if I was to round that a little bit more, might get a slightly less accurate result. But I tried to not round it at all when I was using my calculator. But anyways, what I could do is I can completely solve this triangle as long as I know two pieces of information, one side and one angle, or two sides and no angles. Well, technically, you obviously need to know one angle. You need to know that it's a right triangle. But as long as you know two things, that should be enough to completely find all the rest of the information. And the tools that you need to use to find it are SOHCAHTOA, Pythagorean theorem, and the interior angle property, or if you want to remember it as the complementary angle property as well. And actually, my final little bit here about complementary angles is that let's say I was to take the cosine of angle 40. That in this case, that would give me the trigonometric ratio of adjacent over hypotenuse, exactly that. But what I wanted to mention is, let's say I was to look at the sine of 50 degrees. Notice that the sine of the 50 degrees would be this angle up here. Sine would be opposite over hypotenuse, which would be the same exact ratio that I just wrote. And the fact that those two functions give me the same ratio for complementary angles, that's exactly what the meaning of a cofunction is. Sine of 40 and is always equal to cosine, sorry, sine of 50 is always equal to cosine of 40 as a basic trigonometric principle because those angles are complementary. And there's what we call the cofunction identities, which we'll talk about more in a week or two, which are just identities which relate the functions based on the fact that the angles will always be opposite with respect to 90 degrees. And just as a summary of what I'm mentioning here is, let's say I was trying to figure out the cosine of 22 degrees, or let's say I knew what that was, just as a completely alternate example. What the cofunction identity would always imply is that the sine of the complementary angle is equal. And those two functions are always equal with regards to inputs different from 90. So if you take the input of the first, subtract it from 90, it'll always be equal to the cofunction. And that's also true with secant and cosecant and tangent and cotangent as well, because really it's the same reason. But anyways, that's what cofunctions are all about, complementary angles, which is something that I didn't know for a really long time. And I guess it's interesting and useful if you know when that could be relevant, which is not really that often. SOHCAHTOA way more important than all that. Anyways, in the next video, we'll do a couple more examples of solving triangles using SOHCAHTOA.